All right, let's go through the questions that you've been working on in the last two classes and make sure that we know the correct answers and understand them. All right, so the first question, the boy and girl are riding on a merry-go-round that is turning at a constant rate. So that would mean that omega is a constant. The girl is near the outer edge and the boy is closer to the center. Who has greater angular displacement? So they both will have the same angular displacement. The angular quantities will always be the same on a rotating object, but the linear quantities will be different because they are related to the radius. For instance, the distance is equal to the radius times the angle. But on a rigid body, everything will have the same angular displacement, same angular velocity, etc. So if you're leaving a building and the door opens outward, the hinges on the door are on your right. This is actually just like the door to our classroom. The direction of the angular velocity, remember that's going to be along the axis of rotation, using the right-hand rule to curl your fingers in the way that the door will rotate. We'd have to hold our hands so that our thumb points down, and so that would be the direction of the angular velocity vector. Okay, so this is a graph of angular position versus time. So you might want to compare it to position versus time. And keep in mind that, like, how did we get different values? Like, how did we get velocity, acceleration, etc. from these graphs? The angular velocity, which is going to be the change in theta over the change in time, is going to be coming from the slope. So that's the first thing we're going to look at, is ranking these according to slope. D and E have the same negative slope, so those will be the smallest. A and F are both 0. And then the next, as we're moving up in values, C would come next, and then B would be finally. Angular acceleration would be, is the slope changing? Because that would indicate a change in the angular velocity, which would mean that there would be angular acceleration. The answer to that is no. All of these have a constant slope, which means the omega is constant. So all of them have angular acceleration of 0, so they'd all be equivalent. Okay, so now we're getting into looking at constant angular acceleration. So this disk has a constant angular acceleration of 5 radians per second squared. The time is 0.4 seconds we're looking at. And we're also told that it was initially at rest, so angular velocity initial is 0. So we want to know what is the angle at t equals 0.4 seconds. So we would start with this expression. This is 0. We could say this is 0, so theta is just 1/2 alpha t squared. 1/2 it's 5, not 0.5, times 0.4 squared. And if we do that calculation, we actually get 0.4 radians, and that would be answer A. Okay, so this problem was a little confusing, I think, because of notation. Let's just say that in the way that these questions are, omega naught would be the final angular velocity for the first case. It's not actually the initial velocity, which I know caused some confusion. In this problem, it's best if we use this expression to try to compare our two answers. So basically we have an object, it's initially at rest, it's going to have a constant angular acceleration, we're going to turn through an angle theta, and it's angular, and then it has this final angular speed. So for case 1, omega squared would equal 2 alpha delta theta. So omega would be the square root of 2 alpha delta theta. We're going to call this one omega naught. So this is the final angular velocity for the first case. In case 2, alpha is increased to twice as much, and if it goes through the same angle, we want to know what the final angular velocity is. So here we get omega squared will be equal to 2 times 2 alpha delta theta. So omega would be equal to 2 alpha delta theta. And we'd want to compare omega to omega naught, and if we compare these two values, we would see that omega is equal to the square root of 2 times the omega we got in the first case. Because if we multiplied this number by the square root of 2, we would get this, and that's how we know that. So our answer is D. Okay, so here's an example from our textbook. So our rigid body here is a fishing reel, and we're going to say it's initially at rest, so omega naught is equal to 0. The radius is 4.5 centimeters. And the angular acceleration of the reel is 110 radians per second squared. The time that we're going to talk about is 2 seconds. All right, so given that, if our reel was initially at rest, it had that angular acceleration for 2 seconds, what would be our final angular velocity? We'll use this simple expression from our kinematic equations. And we get omega would be 220 radians per second. So that's how fast it's going at the end of 2 seconds. It wants to know how many revolutions the reel make. That's actually indirectly asking for the angle theta, which we're going to find using this expression. We can let both of these be 0. We get 1/2 times 110 times 2 squared. Now, it's kind of interesting. We get the same number for these two questions, but it's not, we're measuring, there's different quantities. Now I want to change this to revolutions. So I take 200 radians, and I know that one revolution is 2 pi radians. So that's the conversion factor, and I would get 35 revolutions. And then if I want to bring it to a stop in part B, I know it's a little difficult to see here, we would want to know omega final is 0, omega initial is 220, and this is your alpha. So omega is equal to omega naught plus alpha t. T is going to be omega minus omega naught over alpha, and we would get a time of 0.73 seconds. Sorry, I had to squeeze that in. All right, I didn't have to because I didn't realize I had this other page, but in any case, we just did that. Okay, so now we're back to the merry-go-round. The girl's on the edge, the boy's closer to the center. Girl, boy, Here's the center. Turning at a constant rate. And so they're asking who has the greater tangential acceleration. Constant rate means omega equals constant, which means that alpha is 0. And since tangential acceleration will be r times alpha, they actually don't have any tangential acceleration. Obviously, they were trying to have you think about the fact that the girl has the bigger radius. Therefore, her tangential acceleration would be bigger if that wasn't 0. But it is. All right, so here is the DVD is rotating with ever increasing speed. So alpha is positive, it is not 0. How do the centripetal acceleration and tangential acceleration compare at points P and Q? The centripetal acceleration is omega squared r. And so the radial acceleration for Q is going to be bigger than that for P because of the bigger r. And the tangential acceleration is going to be alpha times r. And once again, Q will be bigger than P because of bigger r. So they both, Q has a greater tangential and radial acceleration than P. Finally, we have a centrifuge, 34.9 radians per second squared. So then we're going to find the tangential and centripetal acceleration at 29 seconds. So we need to find out what that omega is at that point. Tangential is going to be alpha times r. And the radial is going to be omega squared r. All right, and so the tangential looks like that. The radial looks like that. We're trying to figure out this acceleration and what the angle is. And we're going to look at this angle right here. And the angle ends up to be 1.6 degrees. And I could use the Pythagorean theorem to find the total acceleration, but they actually didn't ask me. Oh, they did, but I didn't find it. But the total acceleration would be the square root of a tangential squared plus a radial squared. All right, so hopefully this is